Hello, my name is Moody Hadi. I'm the Group Manager of New Product Development at S&P Global Market Intelligence. Today I'm going to cover a topic called Distributed Language Processing Apps for Financial Engineering for the NLP Summit in October. To give you a quick idea about this topic, natural language processing is a contemporary topic in a variety of different fields. In this talk, we'll basically go over a bit of a framework for assessing different machine learning applications and cover even some specificity around sentiment analysis. And that's targeted on basically explaining to stakeholders the trade-offs on some of the different approaches. Then we'll go into two case studies around two applications, one in deep learning and the other in online learning, that are both leveraging natural language processing in a distributed manner. And then we'll conclude with basically future extensions, further research, and open it up for questions and answers. So a quick outline today is, we'll go over quickly what S&P Global is doing, then we'll go into the machine learning techniques, the risk and consideration of different applications, so trade-offs. And then we'll go into sentiment analysis, a similar idea about a generalized pipeline and what the trade-offs of different techniques are. Then we'll go into the two case studies, one on sentiment analysis for documents, the other based on financial statement assignments for documents, and then we'll conclude. So S&P Global has basically four major business lines: S&P Global Ratings, which effectively rate larger public entities; S&P Indices, like the S&P 500, the Dow Jones; S&P Global Market Intelligence, which is the group I belong in, which is focused on providing data analytics to basically a variety of clients in finance, typically targeted towards risk management; and Platts, which is an energy-focused research entity as well. In S&P Global Market Intelligence, some of the risk management applications include credit risk, market risk, and operational risk, in addition to basically supply chain and just general transparency around entities, public and private. So the next area is machine learning techniques and risk and considerations in their application. So machine learning, as a data scientist, you're going to be asked to solve a lot of basically particular problems. Your clients may not have really much of a view on how you go about solving them. So it's really left to your discretion to decide what sort of techniques to solve and when to apply them. So it's very important to really be able to assess the different types of algorithms with the context in mind. So you don't end up over-engineering something that ends up down the line becoming difficult to maintain and may not even scale for different use cases. So you have to keep those trade-offs in mind. Generally speaking, in machine learning, you kind of go through basically data preparation, pre-processing area, cleaning of data, labeling text if you need to basically do some supervised learning in NLP. Model definition, you will basically have different types of approaches you want to test and ways to basically structure them. And then obviously you go into training and testing, so you try the different approaches, do hyperparameter tuning, adjust, show back output on basically what the accuracy and recalls are, and the general ROC. And depending on those trade-offs, you basically decide which technique you want to go with and effectively implement it in production for model use and actually producing predictions. And then as that's already in production, you want to have some form of a benchmark to compare what you've built against what basically another model may be outputting in order to decide when you want to retrain or tweak basically what you've launched. So, this is a typical trade-off problem, where it's variance versus bias trade-off. There's a little calculator you can use in this link to kind of illustrate this. This has really helped my team explain to a lot of stakeholders the difference between some of the sort of the structured models versus the low bias models in machine learning. And really it comes down to the high bias that's evident in basically structural forms, and the low bias that's evident in basically some machine learning techniques. Here we basically use random forest as the machine learning technique, and you can see that basically with the high bias models like nonlinear regressions and quadratic regressions, they generally follow a structural form, but they're not sensitive to basically small perturbations in the data set, so they cannot really adapt. Whereas the random forest technique, which is a typical machine learning technique, which is evidenced by the orange line, is a low bias, so it can adapt to the fidelity of the data. However, it is sensitive to basically reflections into the underlying perturbations of the data generation process, right? So it can actually really twist a lot more compared to the high bias models, depending on the data you're actually getting. So you have to really consider those trade-offs. And I think this is a nice calculator where you can basically play around with it, generate your own data generation process, and try different techniques in real time just to sort of illustrate these trade-offs. In the real world, there is no perfect, basically, model, right? You have to basically decide what the sweet spot is between overfitting and underfitting, and how often you want the model to essentially adapt to the data set when it's appropriate, and when basically it's okay to sort of lose some transparency, but have like the high adaptation process is more important. So these are really competing objectives that you want to keep that in mind. A few white papers that we have on S&P Global is the Perspective of Machine Learning and Credit Risk, a paper that's illustrated there. This is a nice matrix we've basically used to illustrate to stakeholders, business stakeholders, the trade-offs between the different techniques. So obviously the traditional or structured form of general linear models and logistical regressions, their considerations is they are tightly coupled to the data set you have basically trained on. The sensitivity to outliers and transformations, you have to do a lot of feature engineering before you can kind of use them. They require high supervision, but they're very transparent, so with relatively low complexity compared to, for example, random forest, which can deal with polluted data, but it's on the other side, it's more difficult to explain. You have to really kind of understand the accuracy relative to basically well-structured and clean data. It may not really give you as much of a boost as, say, the traditional techniques. But it does require low supervision and has somewhat of a medium complexity, as compared to, for example, gradient boosting, which is, like the random forest, a little more difficult to explain, I would say. Again, low supervision, relatively high complexity. So you want to consider those depending on what your context or business application would be. So to kind of follow the same theme, I'll go into natural language processing, specifically towards sentiment analysis. We'll go over just sort of a very high-level generalized sentiment analysis pipeline, consider the trade-offs and considerations similar to what we did with the machine learning techniques before. So common application of machine learning is sentiment analysis. I think that's the most common one you hear about in the media and the news, and for a big reason, because it does deal with highly unstructured data sets, and it does try to basically find a relevant signal from this unstructured information. So we can really kind of divide them into two areas, the techniques to apply them. One that's basically somewhat deterministic. It basically relies on a bag of words techniques, and one that is supervised but more sort of machine learning oriented or not deterministic, and that would rely on the deep learning aspect, which is more the neural networks, right? So the first step is you do have to basically obviously tokenize convert the unstructured information to somewhat of a structured set, whether it's data frames or data tables, apply some stemming and tokenization on the text itself. Then there you have basically two choices. When there is a reason to, when there is a neural network applied, you'll have to kind of either create labels or find some way to imply labels on your corpus, which is evidence here. And then for deterministic approaches, they don't really rely on that. You can basically run that through a dictionary have some form of prescriptive weight to score the features. In some cases, you can get a little more technical and apply some form of regularization to them. So you can basically give features that are less relevant to your context, a lot less weight, and then you kind of end up with the classification technique. In the neural network side, you have to represent the data into multidimensional space, so you have to vectorize. Once you've decided that the vectorization has a high level of accuracy, you can essentially go into convolutions and long short-term memory networks and basically design your network according to your accuracy and recall trade-offs. And then once you've reached that balance between overfitting, like we talked about before, and underfitting, or bias and variance trade-off in a lot of cases, you've reached some form that you're confident that your network will adapt as information comes. You basically end up into the predictions and classification techniques. Similar to before, this is sort of a matrix that we've used to describe the trade-offs across the different NLP techniques, right? So you've got, especially in sentiment analysis, you've got a plain bag of words approach, dictionary-based approaches. They rely on deterministic aggregations. The dictionary needs to be designed, so there's a lot of manual recalibration necessary. You have to basically build a list of words with weights against them. So it's a high supervision, low complexity on the other side because it's very transparent on how you've calculated your overall classification scores. On the regularization side, you basically can regularize that dictionary. So you reduce the weights on certain particular features that are less relevant. Requires recalibration. You've increased complexity slightly, reduced a little bit of the supervision, but it's sort of a medium state. Whereas in networks, the context is definitely maintained. So if you're very, very careful about the corpus you're using, you can maintain the context and capture nonlinearities quite well. It's a non-deterministic approach. You can basically leverage backward propagation for online learning, for automatic learning. Low supervision, but high complexity. Explaining why a particular article was scored in that manner is more complex than the other two approaches. But it is doable, right, as we'll go into later on. So on the next slide, we'll go into basically a case study about a project that we've leveraged sentiment analysis for documents. So what are we doing? At S&P Global Market Intelligence, we've noticed a very large amount of commonalities in our clients' problems, one of them being that they're sitting on large bodies of unstructured data that are typically specific within a particular domain. In this situation, we've seen that clients have a large amount of public disclosures from Chinese entities. And today, as they kind of look at their portfolios and exposures globally, they have to basically follow on those entities almost one by one in order to find if there was a significant move in their overall financial health of that entity. So the process is very manual, inefficient, highly dependent on human expertise. Obviously, the language does present its own idiosyncratic challenges compared to the Latin-based languages, as well as the areas. So the question here is, can we build a system to extract the opinion from the document, if it exists in the document, and classify it in an automated way so that our clients can basically immediately see the trends that are happening at the entity level, and they can attribute those changes to particular disclosures, public disclosures that those entities have done. So we're not trying to infer the opinion or guess like how this opinion will influence, say, stock prices or influence probabilities of default. It's really just trying to take out the opinion and reflect it, classify it as it exists in the document. If there's no opinion, there's basically no sentiment, right? So in order to do this at a high level, and this is a common theme you'll notice through this presentation, we have basically a large body of image-based PDFs. We have to take that large body, that's our corpus that we have to start with. We have to structure it into some series of data frames, as you can see in the middle here. once you've done that, you do some form of operations, and you're able to essentially generate a time series of basically where the classification of the entity is as their disclosures occur, and somewhat attribute to them at a particular point in time what occurred actually in the text itself. So the first thing is, it kind of goes back to the sentiment analysis framework, right? Since this is going to be a neural network-based approach, you need to have some form of labeling in order to train your network against. So for us, what we've done is in Shiny or Rstudio Connect, we basically built an app, hired some folks to actually go through a selected set of, hired some reviewers to go through a selected set of our corpus in Chinese. And as you can see here, they go in disclosure by disclosure. They basically allow for classification of that disclosure at the article and section level, and they can attribute particular sentences to why they classified that section the way they did. So this way we generate our own data science, and a lot of the feedback basically can be used into the when we go into the network itself and the training series. So of course, this is a manual process, requires a lot of verifications against it. So it goes back to the trade-off thing. There's quite a bit of payoff, especially when it's a difficult problem to solve like this. But I wouldn't recommend it for every single sentiment analysis approach. This is why Bag of Words is very, very popular, because it doesn't require a lot of this sort of heavy lifting. And the deeper and more difficult the problem, the context is, the more sort of idiosyncratic and detailed you have to go through the reviewing and checking of the labeling before you even step into the network design, right? So on the next area, we're going to go into how we did it. And in this case, I'm kind of showing an overview of basically the overall pipeline, which we'll get into more details down the line. The first area we're going to go into is, as we take a document, we basically run it through optical character recognition, convert it in a series of data frames, and we run some algorithms to basically section them out. For each one section within the same article, we run through our network to classify them against our scale, first really relevancy and irrelevancy, and then if it is relevant, classify it against basically positive, negative, neutral, where we're outputting the probability of that classification as well. Then we can aggregate essentially those section level classifications up to the article, and then from article to company and company to sector if we need to, in order to generate this overall time series. So at a high level, this is sort of a very much the pipeline that we're looking at. On a more detailed area, this is showing the combination of libraries we've basically used for this pipeline. So we use both R and Python languages to basically design this. And these are all containerized and used. In this situation, we're using Spark to distribute basically the processing. So we're looking at actually data going back to 2012. Public documents that are going back to 2012. So there's like approximately a few million or so image-based documents that we have to basically process. So in the native language, we basically use Google Tesseract and ImageMagick to do the image enhancement and optical character recognition. Once we have those in some series of data frames, we basically need to run them, do basically section-based processing and boundary detection to figure out what sections, where to cut off the documents are in order to basically kind of chapter them out. Then we've built our actually own, we use JBA to basically do sentence and word tokenization in Chinese. It's an open source library to help us detect where basically words and sentences begin and end. We built our own vectorization model, that is trained on the exact corpus we're using here, which are public financial disclosures by Chinese entities. We don't use it. We tried fast text and some of the other pre-trained networks, and those failed given the context that we're dealing with, which is very finance-oriented in the native language. So we built our own vectorization. We tested it out through sort of an independent set of reviewers to see how our accuracy is maintained and if the analogous terms come back. In this case, we've leveraged scikit-learn and TensorFlow quite heavily. There is an R package. Although this relies on Python, there is a TensorFlow R package as well. Once we've basically knew what our vectorization is, this is when the fun part comes in, and basically we've designed a neural network layer with an input layer embedding a series of convolutions and a series of recurrent layers, an output layer in order to actually classify the manually labeled sentiment polarities out of sample, in and out of sample, in order to generate the score. So once we've done hyperparameter tuning here and we're basically comfortable with the model training and validation, these kind of tie together. The rest is really orchestration and deployment across using Spark into the volume of historical corpus and ongoing corpus that we basically receive. And we use actually Airflow for pipeline management, and then of course these libraries for sort of data in R for data processing and indexing. I think one unique thing about this approach is we use model-agnostic interpretability in order to perturbate the individual features after we classified them in order to provide some form of sentiment attribution on top of the document. Meaning, if I get a particular article, I can tell you which area in that article influenced my classification mostly. And that basically creates an attribution and creates transparency for my users to actually understand why at least why the network classified a particular article the way it did. And that feedback loop can be integrated back into the overall training as users basically see that output. And that's kind of a distinguishing feature that's typically new, and there's a lot of ongoing research around it for model interpretability. But it's kind of, think of it as a way to emulate the bag of words transparency that you have in the other techniques. So this is sort of an example of our apps. I mean, as you can tell, for this product, as you can tell, the typical process for us is once we basically built the model, trained it, ran it through our testing and user acceptance testing internally and sometimes externally, the whole interface to actually interact with the information is built through Connect, and you can actually build that for Python in Dash as well. You've kind of built these apps, expose them to your end users, and they can actually interact with your data in real time before you even go to production, right? And we've gotten a lot of feedback through these basically Shiny apps, and you can see the real live data kind of coming in as we observe the article against a -1 to +1 classification score. They can click on a particular area, see which basically areas influenced it. We can aggregate it up into basically sector and other sort of hierarchies, and even basically for a single portfolio, actually look at a storyboard of basically what's going on in my portfolio. What are the significant key events in my portfolio that I can highlight? Think of it as basically in those chapters for those entities, which sections were the most relevant, had the highest classifications in there, so that you can quickly kind of, if you're a user who's covering basically around 12 or so, 20 plus entities, you can quickly iterate through the storyboard to see the significant events that are occurring. The other advantages, when there are significant changes in, say, for example, in this case, in risky behavior, these are entities that experience default that we basically kind of, they're quite large entities that have experienced news-related like events. You see that our classification is very well tracking those events. And in this corpus, you see a very typical pattern is when basically an event gets announced that there is some risk of default or restructuring. There's a lot of announcements around why, what's going on. Eventually, you see it revert back because usually in this area with state-owned entities, they figure out a restructuring for their debt holders, and they revert back. So they effectively think of it as a reemergence in the U.S. and European markets. So the very typical pattern of severe distress and then some form of reversion in a lot of cases. Yeah, but this generally tells us that we're able to extract the opinion if it exists in a document in Chinese for this corpus in a very, very sort of unbiased manner. just a direct reflection of what the company said about itself in that document with transparency around it. So in the next area, we're going to go into the case study around financial statement assignments that are document-based. Very similar story to before, except it's not in Chinese. So in this case, we're basically looking at a way to assign financial statement line items that are coming from proprietary or private companies, and how do we basically take that balance sheet, income statement, cash flow statement line items, assign them to our kind of called dictionaries, or our method of basically structuring this information, and then running credit analytics and scoring models against those entities for our clients to be able to track them, right? So, the problem is basically non-financial corporates and banks have exposures to small and medium-sized entities as part of their supply chain and lending activities. A lot of these financial statements, you can go on the internet and pull them. They're not public. They're proprietary. They're given bilateral between our clients and their counterparties. We're here as a software provider basically assessing, helping them create this using our models to basically manage their exposure. Today, the process is largely and highly human dependent, meaning you physically have a screen and a person looking at the image document, typing in line items one by one into, say, an Excel sheet, and then running some form of scoring against it in order to manage them. So it's very inefficient, costly, and slow. Knowing Excel is difficult to audit and store those changes. So generally speaking, the process is somewhat unreliable and is prone for efficiencies. This is sort of a technical term, spreading financial statements. You may or may not have heard it, but basically the Risk Management Association defines it as a process by which a bank transfers information from a borrower's financial statements into their financial analysis spreadsheets. And it needs to be input correctly, and the spreadsheet has to have some meaningful financial reporting to assist the bank in managing their exposures. This is basically what this is. So it's a method to transfer information from the borrower into a credit scoring algorithm. Right? So what does this mean? What does it really mean? We're basically looking at a bunch of documents that are not really structured. They're very, in some cases, they're watermarks and image log, and we have to transfer them into something that for public entities and for entities that we have very much structured information should look like this. So as a data scientist, this is kind of the look you kind of end up with, right? Like, what do I do? So at a high level, it's quite simple, right? We've already built, even from the prior process examples we already have a method to do optical character recognition, image enhancement, and table detection. So we can basically convert this mess into basically a structured metadata output. In this case, we by the way, deal with multiple languages. In this case, a dictionary approach could actually be very relevant because your taxonomy is relatively limited. So, and even across English, German, Dutch, different languages, Latin-based typically in this case. So you can build dictionaries that are going to extract those item descriptions and assign them semantically using our taxonomy to the taxonomy that basically our market intelligence financial statement chart of accounts would look like. When there is some fuzzy matching, you can allow the user to basically verify and edit them as it exists, which goes back into a reusable dictionary and auditing. Think of it thumbs up, trash, moving around these assignments so that you can integrate online learning back into the whole process. And then effectively, once you've structured this information, you can easily produce through our existing stack of technologies, basically send it into a structural model that will score for probability of default and implied credit rating. So it's basically at this point, from here to here, it's more or less business as usual, right? So to go over the overall architecture, again, you notice some commonalities with the other exercise, except this is an application in NLP, but using dictionary approach. You've got basically native language documents coming in. You go through extraction, which is a combination of optical character recognition and image enhancement and rotations in order to handle basically very noisy documents that come in. This is Python-based libraries. Once you have those structured outputs, you can run table detection against them. Once you have those lists, you can basically send them back into the processing assignment engine, which relies on the mnemonics and the taxonomy to basically see and look using different sort of set of voting algorithms across different layers, like I've itemized here, to see when I have a particular phrase or group which is financial focused, can I match it to my dictionary, in which case I already have a mnemonic associated to it. And that we basically do a voting algorithm against the different sort of Latin-based string matching algorithms. We track the online learning in case there is a user basically verifiable output that comes in and goes back into our reclassification engine, and then goes into the business as usual piece, which is in .NET and Java, that allows us to take that structured line items and score them for probability default. And then the rest is easy. So like the rest is basically simply we're going into exposing a JSON and AJAX output to the UI itself, and then there's an Excel plugin so you can basically manipulate the items in our models. At a high level, from an architectural standpoint, you've got a user interface that's basically going through the users uploading documents as they see them on demand. A lot of image-based processing that we store some data in S3 on our private cloud in order to just process it. Once we process it, we check it off. We're using Kubernetes to containerize all these basically objects and Docker to store them. And these are our endpoints that are API calls to any other system. It's a microservice that has one endpoint, one input, one output, and it processes. We leverage a lot of horizontal scaling. So with a queuing mechanism, this is first in, first out approach. This is using Kubernetes to basically handle the horizontal, to basically create the horizontal scaling for us as we package every container and scale depending on demand. We're getting a series of post requests. We have a centralized queuing layer that basically decides it's a first in, first out algorithm, but adjusted for the size of the documents as we observe them. And we can keep it increasing elastically depending on demand. This is an example of the Shiny output. Again, same process. We basically expose this in some UI, in this case Shiny, Connect. You can easily do this in Python as well using Dash and different packages there. But the point is, it goes through a very rigorous user acceptance testing, verify that the whole workflow is working end to end, and then once we know that this is actually ready, we migrate all our containers over to production into the UI in production. So in conclusion, these are further extensions that apply to both cases, whether it's deterministic bag of words or deep learning. So BERT, I think, has gone a lot more, bidirectional transformers have gone a lot more further research than even when I put this together. Elmo for embedding languages, but a lot of extensions in basically risk signals, and NVIDIA's built Rapids for basically manipulating data on the GPU itself, so it can scale more, and obviously transfer and online learning, which is really important for these type of supervised type models, right? The one that is close that I encourage you to look at is really LIME, which is a locally interpretable model agnostic explanations. Essentially, it's a way to perturbate features in order to explain, depending on your model, what basically occurred there in order to create transparency around what the network is doing. And this is really a very, very strong area that's important as machine learning keeps evolving in time. In conclusion, I'm going to open it up to Q&A. Thank you for listening to me as we're going through this. This is my collaborators, and in S&P Global, we continue to use cutting-edge technologies and techniques to improve our clients' day-to-day workflows. Thank you.